Hello everyone, welcome to the new session of 5G non-standalone training. Today's session will be covering about the 5G basic planning, and I'm going to split this session into 2 or 3 videos to cover all the related or most of the related aspects of the planning in details. So let's go through the contents. As you can see here, this is the main context which we are trying to cover most of it in the upcoming videos. The first part, it's about the NR operating band spectrum. I will just give you a brief introduction about what kind of available bands is available in NR, what is the differences between low band and mid band, and for example, that we know that low band can be used for coverage purposes, or mid band and high band can be used for capacity and so on. So this one, and also we'll go through how to verify or check the existing bandwidth or spectrum from the UE logs. Then we'll be going through that how to configure or what is the theoretical understanding about the SSP center frequency or the channel bandwidth center frequency and so on. Then we'll give a very good or a very interested inputs about the SSP location. Whenever going to configure the SSP location, you need to understand what kind of impact you have it in the performance, even throughput or coverage or all other aspects. So this one will be covered in details. Then we'll go through this neurobiology will be covering under the same part of an operating band. Then we'll go through the slot format, and this is one of the most important topics which you need to really understand because it's kind of new compared to the 4G. It's kind of similar, but it's having many new inputs. So actually, today's session will be mainly about the slot formatted. So slot format, we'll be starting with this part, and we'll be covering under this part many different inputs. Like I'm trying to cover the theoretical part, not only the what kind of planning we can do, but just to give you a very good understanding about it. So for example, first we'll go through duplex scheme, then about the configuration types of slot format, which being introduced in NR, then about something called cross-link interference and the remaining 4G NR coexistence, and what is the impact in the performance in general, either latency or throughput or coverage whenever you change the slot format. So this is what we're going to cover. Then after that, we'll go through that in the next sessions also about the beam selection, BRACH planning, and all other PCI and so on, neighbors and tracking area. So now let's jump to the part of the slot format, which is going to be discussed today in details. Later on in the other session, we could discuss about the other inputs as well. But before jumping to the slot format, I'll just to highlight here what it means by this kind of stars and the red arrows and so on. Whenever you see this red arrow, this means that this kind of planning inputs can impact throughput or coverage. And anything highlighted by, for example, orange star, this means this can be done through planning tools or through planning or Excel tools, or you can even follow the existing 4G network in the non-standalone. For example, for tracking area update, you don't need to do any planning. You're just following the 4G. 4G will be the same. You don't need to. There is no tracking area currently in the 5G non-standalone. This one might be needed whenever you go to the standalone. And the RACH planning, actually, this is depend on the RACH type you are going to use. For example, if you're using long format, which is format 0, this is similar to 4G, so you might be able to utilize the existing or reuse the existing RACH planning in the 4G and the 5G network. So this is just the last part. Now let's go to the slot format. Okay, so this is actually the introduction first about the slot format. Actually, the main idea that first of all, I would like to tell you that this kind of slot formatting planning, this is mainly will be in the TDD, which is the time division duplex. So let's first go through the duplex scheme to just explain what are the differences, like just to recap our knowledge about it. For example, the first one here is explaining about the TDD time division duplex. As you can see, this is the frequency domain. This is the time domain. So we have only a single frequency in this part, in this TDD, and the resources is being allocated in the time domain. So it's single frequency, but the separation between the downlink and uplink resources or frequencies, it will be separated in the time domain. This is mainly what it means by the TDD. So in this case, you'd like to have a planning of how many resources, for example, if you have, let's say, 20 slots or 10 subframe, how many will be used, for example, for downlink, how many for uplink, how many for guard band, and here is where the slot format will come into the figure. For FDD, it's kind of different. As you can see that here we have two different frequencies, and each is being transmitted. So this is only separated in the frequency domain, but they are transmitted at the exactly the same time. So here we can say that we don't have a really direct correlation with the slot format planning, so that will be mainly TDD. The last part, it's about the FDD half duplex. This is actually exactly the same, but as you can see here, The main difference is that you have two different frequencies, but in this case, there is the uplink downlink separation will be in frequency time domain. As you can see, for example, uplink is being transmitted here, while nothing is being done in the downlink frequency. It will be like nothing being transmitted. And the opposite way around, whenever there is a downlink, there is no uplink. And actually, just to highlight, this is a proprietary of devices. The network itself is supporting the full duplexes, but if the device is, for example, supporting a particular frequency in FDD, but supporting only half duplex, so the GNB will follow this kind of sequence whenever it's going to schedule the resources for this particular user. So again, this half duplex is more about the UE capability itself, not related to the BTS or the network. So actually now let's go through the slot format, what we're going to discuss today. This is the main inputs. As you can see here, we have 3 inputs. First of all, they are going to go through the NRTD slot configuration types. This is very interesting because this is something new. Actually, we have 3 types. First one is the static TDD, which is exactly the same as the 4G. We used in 4G, the main difference is 4G is being fixed, means that you will have a fixed downlink slots, uplink slots, and even symbols and so on. You cannot change it at all. Once you configure it, it will be fixed all the time. While in NR, which having more flexibility now, it's introduced this kind of semi-static, the TDD, or even completely dynamic, which can change the slots or the symbols within the slots to be downlink, full downlink, or mixed and so on. And we'll go through this kind of details. However, this part, like whenever it's going to use this, is can introduce something called cross-link interference, which we are going to explain as well. And there is some main consideration we usually consider whenever going to make the slot format planning. For example, the first one, it's about the government. If any national regulator, for example, being a specific request coming from the government, and this is might come whenever you have a close boundary with neighbor countries, so they might try to align the slot format indicate slot format planning between the different countries, operators, and vendors. And this is especially if you're using the same frequency. So this is must be done because again, if it's not aligned, again, it might cause something called cross-link interference, which we're going to discuss. Then we're going to discuss about whenever you have 4G and 5G operating, for example, different sites with the same frequency, what it means by coexistence, what is the relation with the slot format, and what we need to do. Then we'll again explain about the cross-link interference, and this is like will clarify or emphasize the meaning or understanding of cross-link interference. Then the last part, it will be explaining the impact of the assessment in general of different TDD slot format configuration, so you'll be very aware about what is your current situation in the network and what you can recommend and so on. So now let's move to the first part, which is related to the slot configuration. First, I will give a quick recap of the 4G, then I will compare it with the 5G. Then we'll go through one by one the details for the 5G part. So the first part here, it's about the subframe, or we can say subframe configuration or subframe and slot configuration for the 4G part. If you remember, first of all, in 4G, it was about the subframe assignment. It was, we have defined the 3GPP, defined 7 uplink downlink subframe configuration, and this is being fixed. There is no change. So you can only select one for your network. The most common one, it's this one, which is uplink downlink subframe configuration, which is 1 to 3, means you will have 3 for downlink and 1 for uplink, and the remaining 1 will be for the duration of 5 milliseconds. So each one will having a subframe. So the remaining subframe will be, for example, a special slot. So for example, here, the most common used one is configuration 2, which is if you click here, this is the one we are going to use here. As you can see, the first 5 milliseconds will have 1 for downlink, then 1 special slot, then 1 uplink, then 2 downlink. So this is a 5. Then it will be repeated again for the next 5 milliseconds. So this is actually what it means, but this is, again, it's fixed. We cannot change it. Then now for this special slot, again, we need to have something called special SSP configuration. It's special sub configuration. And again, 3GPP defines also a set of configuration, which is up to 9 configuration. The most common used usually is either 1 or 7, 5 or 7. And here I'm giving example for 7. 7 means what? That within this, for example, subframe, it having 14 symbols, if you remember. So this will give you the distribution for the downlink, uplink slots, and guard band within this particular symbol. For example, downlink means all the symbols within this one will be downlink. And uplink means all the symbols will be uplink. But the special slot, it will be mixed between downlink and uplink and guard band. So this table of configuration, again, you can give it a fixed configuration. You cannot change it once you set it on the network. For example, you're given 10 to 2. This means you will have 10 for downlink, 2 for the guard band, and 2 for uplink. So this is how it will look like. As you can see here, this will be 10 for downlink again, and 2 for the guard band, and 2 for the uplink. And again, keep it in your mind, this configuration is fixed. Once you give it to the network, you cannot change it. The network will keep this configuration all the time between the sites, and the user will being to able to receive the downlink or transmit the uplink within this particular slots or symbols. So now let's now move to the 5G part to give you a quick explanation about it. Then we'll go through the details of each and every single configuration of the new configurations being introduced in 5G. So actually, this is the 5G part. The 5G part actually, again, it's having a similar figure compared to 4G, which being that but this time it will be considering in slots. As you know, the scheduling in the 4G and 5G is being based on slot, not subframe. So here, for example, if you're using SC subcarrier spacing 30 kilohertz, this means you will have 20 slots per frame. So each slot can be even downlink or uplink based on the configuration which you have it, and it can be even being something called flexible. And this one within flexible, it can be having a mixed symbols as shown here, for example. So the main difference is about between the 4G and 5G, that the 4G can use the exact same concept as the 4G, which is being static. You can configure static resources, for example, 8 or 8 for downlink, 2 for uplink, for example, like that. This can be for the static, and it cannot be changed if you give it static from the beginning. Or it can, now the NR introduced to new concept, which is called semi-static allocation or dynamic allocation. The semi-static allocation, it can change some of the flexible if you kept it during the static allocation in the beginning, you kept some of the slots as flexible. This can be later on being dynamically changed by the network, but only for one time. For example, to change some of this flexible symbols even to completely downlink or mix it and so on. And we'll be discussing this part as well to show how it's been working. Then the last part, it can be dynamic. The unit B can change this one from, for example, initially it can assign this kind of configuration. Then again, for the same slot, after some time, it can change it, for example, to completely downlink, all downlink, or partially downlink and uplink and so on. This is the dynamic allocation. But again, dynamic allocation can cause something called cross-link interference, and we'll explain this part as well. So now let's move to the static allocation and move through one by one to see the details about it. So before moving to the details, I'm just explaining quickly here. Again, the main difference is that the 4G is fixed. You cannot change it once you configure it. 5G, you can have the same as the 4G as fixed, or you can keep changing this flexible to whatever you need, even for the semi-static, which would be like you can change it with a specific configuration for this flexible, and the dynamic will be changing those based on the network load and other inputs or factors, where the unit will decide whatever of symbols is going to be allocated within this some flexible subframes. So now moving forward, this is the first type of the slot format configuration for the TDD. Here, it's, as I mentioned to you, it's exactly the same concept as 4G, where you give a fixed configuration. You can even assign it for all the slots which you have it, and then within these slots, you can have a special slot, and again, you can give it some particular symbols. So actually, if you look into this table on the left, this is just the parameters which are being mainly used whenever you're going to allocate the resources. But usually the operator will give you directly, or the vendors will give you directly, you will not make, for example, here you have the transmission periodicity or downlink slots, downlink symbols. Each one you are giving a fixed configuration for each and every single parameter. No, it's not like that. Usually the operator will give you the final figure. For example, in this example, I'm giving that this vendor is configuring 7 for downlink, 1 for the special slot, and 2 for the uplink. So this is how it looks like. It's called, like, for example, TDD pattern. And as you can see, the parameter is called common, and this will be static all the time. So for example, in this one, as you can see, if you go through the parameters which I have it here in 5G, we have something called 2 patterns. For example, pattern 1, if you can either having 1 pattern or you can have 2 patterns. So let me explain what I mean by this. First of all, if you have, let's assume that you have 1 pattern, which is the example which I have it here, and this is the parameters between this part. So what it means by these parameters, first one is called transmission periodicity. This one actually identify what kind of period you're going to have for the configuration you are going to configure. Let's assume that you have here configuring here, for example, 7 downlink slots. So this is, for example, will be repeated every transmission periodicity. For example, if you give it 5 milliseconds, this means this 7 downlink slots will be repeated every 5 milliseconds. I will explain it now with examples. But the downlink slots, whenever you have, for example, 7, it will it will be configured at the start of the duration. For example, if you have, assume now you have 7 slots here as this example, so this means you will have 7 slots at the start of the duration here. Then you will have here the number of downlink symbols. Let's assume that you give it, as we mentioned here as well, 6. This means that the slot which is follow those 7 slots will having 7 symbols of downlink. So for example, this one, you have 7, then the number of symbols, assuming now it's being configured as 6. So this particular slot, which is following the downlink slots, will having 6 symbols as showing here. So this one. And now going to the uplink here, for example, you are giving as mentioned here 2, for example. So this one is starting from the end. So you need to go to the end of the transmission periodicity, for example, at the end of 5 milliseconds, and start counting 2. So it will be here as 2 to uplink. And again, you will have this one, which is the uplink symbols as well. As you can see, as defined here, uplink symbols define the number of uplink slots, symbols, sorry, defines the number of uplink symbols within the slot precedes the slot uplink slots. For example, this one precedes the uplink slots, right? This one, which is F. So now, again, it will be configured at the end of this symbols, as mentioned also here. So, for example, you are giving here as 4, so you will have 4, and all the remaining will be considered as a guard band for the remaining here. And in case, for example, here you have only, assume, for example, you have 5 slots. So this means you will have 2 flexible here. It will be kept flexible. There will be no change flexible here. This is in case you are giving this kind of configuration. So actually, the message on the right here, this is how you can verify from the UEDT logs. For example, assume that you have a benchmarking between operators and you would like to check what kind of configuration being used by the other operators, or even to verify it in your network if you did any change. So during the HTTP addition, this configuration will be delivered under our serial configuration message. You need to search for something called TDD uplink downlink configuration common, which is exactly the same as this one, and that you'll find that it's exactly finding or giving the exact same parameters we're showing here. The example I'm going here, it's used to have one pattern. So this means if you have only one pattern, the pattern will be repeated every BDST, or for example, every open 5 millisecond, depend on the settings which you have in the network now. So for the example here, I'm showing it as 5 millisecond, and here is the parameters. You can see here MS5, this means 5 millisecond, number of downlink slots 7, so this means 7 downlink slots, and you have number of symbols within the slots which is follow those 7 slots, which means slot number 8, which we consider as S special slot, while having a 6 symbol within this F or S special slot or flexible slot. Then the block slots will be 2, as we mentioned. Here it's showing 2, so these 2 slots, and you will have 4 symbols. So the final configuration will be like that. You will have 7 for the slots, and we consider this one in the written or whenever you write it as 7 here, and this one will be S, which is special slot, and then you will have 2 for the uplink, which is called A2. Usually this configuration called as A2. And the special slot or special button or flexible button, it will be 6, right, for downlink, which is 1, 6 for uplink, and the remaining, which is 4, because you have 14 symbols, it will be for the guard band. Okay, now let me explain what it means by pattern 1 and pattern 2. So when I told you that, for example, if only one pattern is being included within this message, this means the pattern repeats periodically based upon the configured transmission periodicity. This is even if it's only one pattern. Assume now you receive one pattern here with particular configuration, then you have pattern 2 as well in the same message, okay, with another configuration. So what will happen in this case? If 2 patterns are included within the message, so that's then the second pattern will follow the first pattern. For example, the first pattern will come first, then the second one will follow the first one. Okay, this is the first part we need to do. And the pair of patterns repeat with a period of equal to the period will repeat. The period will repeat for a period equal to the summation of this one, downlink transmission periodicity, and the downlink transmission periodicity of pattern 2. And one important point as well, or note, TDD specifies that the sum of the 2 patterns for this one, for the periods of these 2 patterns, must divide into 20 milliseconds. For example, assume that you configured as the first pattern 2 milliseconds, and this one 2 milliseconds. So this can be divided by 20 milliseconds. But if you divided the first one as 1 millisecond, for example, and the second as 2, this cannot be divided by 20 milliseconds, so this is not allowed. TDD will specify that this will be allowed. It must be divided by 20 milliseconds. So this is how, if in case you found different patterns in the network, this is how you can do it, as I just explained. So now let's go to the next part for about the semi-static allocation, then the dynamic allocation. just one last part before getting to the semi-static allocation. This message also, if you are working with 5G standalone, you find it in SIB1, System Information Block Type 1. Just to let you know as well for the standalone, for example, as mentioned in this particular comment here. So now let's move to the next one. So now this is about the semi slot assignment or semi slot configuration. The first one was about the static. Actually, the very important comment which I would like to tell you. For example, assume that from the static one, which is, if you remember, the parameter called TDD uplink, TDD downlink configuration command, assume this was your configuration. It left this kind of flexible slots here, and this green one and move one, this is the special slots which are having a specific symbols or symbols for downlink and so on. So assume this was my configuration from the common one, which is having a static allocation. So whenever the semi-static is going to the figure, it can change within only the one which remain as flexible and the one which is being flexible also or being used as a special slot for symbols. But whatever being assigned during the slot, for example, the static allocation which is being downlink or uplink is explicitly mentioned as downlink and uplink, this is cannot be changed at all. This is will be kept all the time like that. So this means that this kind of semi-static will be changing within those particular flexible slots to, for example, a particular configuration or fixed configuration which we need to configure in the network. For example, as you can see here, this is it's called first of all called TDD uplink downlink configuration dedicated, and this is usually also delivered by the RSC configuration message whenever the network see the needs for a particular users or cell to configure or change the configuration for those flexible slots based on the demand on the network or so whatever, and based on the configuration we're giving as well, it will start sending RSC configuration to the user to send them the new configuration about this flexible slots. So as you can see, for example, here, this is called a slot specific configuration to add to mod list. You have a slot index. So this is explaining that, for example, the number of slots which we require to change. Here it's showing up to 320 because we can have 320 slots whenever you're speaking about the higher SCS, which is 120, 140, and so on. But currently it's being fixed to 80 only, 80 slots only, which is up to 60 kilohertz, as I remember, or 120. So this is giving you the slot index, for example, which slot needs to be configured. So for example, let's assume it's highlighted this particular slot, let's say slot 8, for example. And now within the slot 8, it will tell you what kind of symbols you are going to have. For example, all will be downlink or all will be uplink, or how many for downlink, how many for uplink. And it's giving like that. At the end, it will change the remaining. For example, let's assume it's giving 6 for downlink and 4 for uplink, so the remaining 4 will be considered as guard band. So this is just to configure this particular flexible slot. So in this case, it can change. As this example, for example, here it's assumed that, as I mentioned to you, that the first one here for this green one highlighted here, this actually was being configured partially as number of symbols during the slot static allocation. So it's considered like, for example, this 6 as downlink and the remaining was flexible. So whenever this static configuration came, it changes this one to complete downlink. So now it will change this one to be all downlink. So this one will be all downlink. And this flexible one, it will be also changed to all downlink. And for this, the third one, which is flexible one, here it's considered as to keep only 6 for downlink. As I told you, whenever the number of downlink symbols coming as 6, for example, it will follow for the last slot which is being indicated as downlink. So this one now, it will be coming here as green as well, which is having partial number of symbols to downlink. For example, here 6 downlink and the remaining for flexible. And this one, it didn't change it, the configuration whenever the GNB decided. So this one will kept as flexible. It will be reserved resources. There will be no transmission or the user will not be receiving or transmitting anything about that part. It can be used for any other purposes. For example, whenever you have dynamic spectrum sharing, so this can be reserved for the transmission for the 4G side within this particular area or frame. This is as an example. Now for the other part here in the last three, or the last four, the GNB also decided to change. The first one we should move from the right to left here. So for example, the first one here, it was partially also configured with uplink and the remaining was flexible. GNB decided to change it all to be uplink, as you can see here. This one flexible also changed to all uplink. This one flexible changed also uplink. This one changed to partially, and this partially will be also as same configuration. For example, 6 for uplink and the remaining will kept as flexible. Still, you can give downlink and uplink within this part. It's up to you. This can be done as well. It can be, but it's already configured here, so it cannot be in the same because already configured in the beginning for the downlink. So actually, what will happen? This is now was a common one, which is coming in the static figure, which we explained in the previous slide. And now this is the dedicated image. So it will combine both of them, and this will be the resulting of the semi-static pattern. So this will be the resulting. This is what the user will see. Will be this is all downlink, and this will be partial full downlink, and this will be flexible. Then we'll have this one, which having no transmission at all. Then we'll have this partially also for uplink, and the remaining will be flexible. Then all the remaining will be for uplink. So this is how it's being changed. It makes it both of them and give you this kind of results. And actually, this one, I didn't see it yet being used by any of the network which I worked for. So please, if you see this example as a practical, you can also drop a comment and add your experience in the comments. So now let's move to the dynamic part as well. So now for the dynamic part, as you can see, it's actually working on the remaining flexible slots, which is being left over from even the semi-static or from the static configuration, whatever flexible slots. But the main advantage of that part that it can dynamically change the slots. For example, it can change this a slot. For example, let's say it's having 14 samples. Sometimes it can make it the all downlink or all uplink or partial downlink and uplink. This can be dynamically changed based on the load or many other factors in the network or the services which is being introduced. For example, if you have services require higher latency, so it might give you more uplink samples within the downlink slots, as an example. And if you have heavy downlink, so it can give you this one as all downlink, or heavy uplink can be all uplink as well. So this flexible can be dynamically changed as well. As you can see here from that part, first of all, this is being done or delivered through the BDCH, like something called DCI format 2. This will be the remaining samples as mentioned here can be directly reconfigured using DCI format 2. And first of all, as you can see in this parameter, it's called slot format indicator, something called first SFI RNTI. So each user will be allocated with this SFI RNTI before receiving this kind of DCI information. Once you receive the DCI information, this DCI information to format 2.0 provide this is U group comment signaling. So it will be sent for a group of users, which is allocated with the same exact SFR RNTI. But each one of those users might having a different slot format indicator, by the way. For example, here in this particular parameter, which is called position in DCI, which is also being delivered, or the settings will be delivered in the messages within the DCI format 2.0. This one can, for example, having a specific value, which is specified the location of relevant slot format indicator. For example, and this one will take you, once you have this SFI format being identified, it will take you into 3GPP. It will be like a pointer towards the 3GPP table to tell you which slot is going to use which symbols. For example, it will indicate that this particular slot will be used this SFI slot format indicator 0, which means that this particular slot will use all the symbols will be used as downlink. This can be, as you can see, 40 symbols. And we have a total of 56 combination, and also we have combination of 250 and 256 reserved. This is like not being used. So currently the 3GPP supporting up to 56 combination from 0 to 56. So this kind of flexible format can be using on any of these combination, whatever based on whatever the GNB decide based on different factors like such as the services, load, and so on. So these kind of flexible slots can having a dynamically change and within the symbols which are being occupied by this kind of flexible slots. And again, the dynamic can only change on the remain flexible or partially configured as downlink and uplink, but it cannot touch whatever being identified as downlink and uplink. So it will be only working in this area. So now let me give you a quick example about this part to show you like how it can be showing, and also I'll be showing the complete 3GPP table just to give you more details about it. So this is also whenever you need to look into it, this is the table number, and this is the 3GPP version whenever you need it. So this is a complete 3GPP table, as you can see here. It's up from 0 to 55 combination. For example, the first one 0 format SFI format 0, it's having all the symbols as downlink. Format 1 having all the symbols as uplink, and it will be different from one to another. And this 56 to 54 is being reserved, so not being used currently. So I'm giving you now an example. Assume now the GNB decided to change this kind of format through DCI 2.0 for users, for a particular user. For example, this kind of slot. It requires, for example, to use this kind of slot format. Let's assume SFI 28, for example. SFI 28, for example, let's assume that GNB is now saying that this particular user is demanding a very heavy downlink traffic. So now it will require to give him more downlink symbols, as you can see here. So, for example, it's using this kind of slot SFI28. It will be delivering this to the users, pointing towards this particular combination, which will tell him now you will have 12 symbols for downlink, as you can see here, 12 symbols, then one flexible and one for uplink. This is in case of SFI28 being addressed. Assume now another user is having a very heavy uplink. So in this case, this F will be changed to, for example, combination, which is slot format 34, which is this one, which is first one downlink, then flexible, and all the remaining is being uplink. So this can give higher also throughput. Assume now you have a slot aggregation. For example, assuming that you have from mobile broadband heavy downlink transmission and you require even more slots with more downlink slots. So even this can be done through the DCI format. So for example, it can combine this SFI0, which is having all downlink, with, for example, SFI28. So it will tell him, for example, these two flexible symbols with flexible slots will be using will be their slot format. The first one will be completely downlink, and the first one will be 12 for downlink and one flexible and one for uplink. And again, you might see this in many different documents and so on. As I know, it's not currently being used yet. This can be used in the future to be having more advanced allocation for the resources. But this is kind of having some risk, and it required to use in particular scenarios where is the cross-link interference come to the figure, and I will explain now the meaning of the cross-link interference and how it can be caused by this kind of dynamic allocation, or also what kind of other factors can having this kind of cross-link interference. So now let's move forward to the cross-link interference to explain how it can be caused by dynamic, and also what other causes can make this kind of cross-link interference. So in this figure, as you can see here now, this is explaining the concept of cross-link interference, which might cause in some scenarios if you have this kind of dynamic location in the network. Assuming now you have two different cells, cell 1 and cell 2, and this cell 1. And assume that within one slot, the GNB decided to give this downlink allocations within this slot to be 12 downlink and one guard band, and for example, or one flexible and one uplink. While the cell 2 decided to do the opposite way around, to example, to give one downlink, one guard band, and the remaining to be uplink. So what will happen here? This is, for example, a macro size near to each other, or even within the same site. What will happen here? The downlink slots will be interfering in the uplink slots and the opposite way around, because now we have different transmission. And as you know, the TDD now is like a kind of hub duplex. So usually you should be having only one transmission either for downlink and uplink within this slot. So in this case, the frequency of the downlink, the downlink will be interfering with the uplink. And this is where the cross-link interference will come into play. For example, assume now this cell 1, which is a downlink centric slot, transmitting downlink at this particular symbol, while the uplink here, this one is using for uplink. So this cell 1 will cause a cross-link interference. As you can see, this one transmitting the downlink signal, and the same one, this one, the user is transmitting uplink using the same frequency. And as you know, the power is much higher in downlink. So this can cause a severe interference in your uplink. So this is actually one of the things we need to take care of out of it. So this can called cross-link interference, and this from point 2, this will be from BTS to BTS, as you can see here. The second one, for example, which is exactly the same concept but the opposite way around. For example, assume cell 2 now. For this one is transmitting uplink, right? So here there is a transition of the uplink. So this users will make interference for the downlink which is being received by this particular users. So the uplink of this users will interfere the downlink of this users. This also will have a big impact, but it's not like the downlink to uplink. So usually the uplink interfering this kind of cross-link interference would be severely impacted. It will be severely impacted if you have this kind of scenario in the network. So that's why the dynamic configuration, we are more recommending to be used, for example, in small cell indoor scenarios where you have less macro sites, and for example, this can be done only within one site or one cell, where it can be more controlled and avoid this kind of scenarios. So this is the first case of cross-link interference. The second case of cross-link interference, it can be, for example, you can have a propagation delay for the slot. Assume that you have a static slot, all is being fixed between the source and target, but there is a propagation delay due to, for example, duct. So you can see again this kind of scenarios where there is some shift in the signal. Assume that both of them was exactly the same, but because due to the duct and propagation delay, this might be a delay in the frame. So this can again cause cross-link interference, and this can be mitigated or mitigated through one feature called remote interference management. I did a trial for that part in 4G before and 5G as well, but at the 5G, whenever I did it at that time, it was not that mature. So you might look into that if you have this kind of scenario for the humidity or the ducts in general in your area. The next scenario, actually, it's about, as you can see, for the same cross-link interference, can be operating whenever, assume now you have in your network a coexistence between the 4G and 5G. What it means, assume that you have one side operating only with 4G TDD frequency as an example, let's say 2.6 of band N41, and the 5G side as well as a neighbor operating with 5G using the exact same frequency at that one. Still, the network is not continuous there. So, for example, assume now you have the same frequency being shared by both of them, but for different sides. So, in this case, you need to align the same configuration between the downlink and the uplink to avoid this kinds of cross-link interference. Now, for example, in the example maybe here, assume now the 4G here, as you can see, it's showing that you have here the configuration which is being fixed for 4G, which is 3 to 1. The one for downlink, 3 for downlink, and 1 for special slot, and 1 for uplink, as you can see here. And now this is the configuration for the pattern, static pattern for the 5G one, which is using 8 to 2. 8 to 2 means 7 downlink, then 1 flexible, then 2 uplink. As you can see in this particular area, there is a cross-link interference. So downlink is interfering on the uplink and the vice versa. So in this case, you need to be very careful whenever you are going to make the configuration for the NR. So what you need to do, either to shift this one by 3 milliseconds to make this one start from here, start from 0, the frame, I mean, the frame is starting from 0 millisecond, or you can shift it 3 milliseconds, or you can change this configuration. So let me show you from, for example, instead of 8 to 2, you can make it 4 to 4. So let me show you the both examples to explain it more. This is as a solution for the NR. So as you can see now, this is the NRTLT coexistence. So in case this is a 4G, as you know, it's 3 to 1, downlink, uplink, special slot, then uplink, then 2 downlink, and beat it every 5 milliseconds. So in this case, this was our scenario, the previous one, which is having 82. We just give a frame offset by 3 milliseconds to make sure that this one will be exactly aligned with the 4G. So this is shifting the frame by 3 milliseconds to make sure it's aligned. As you can see here now, downlink is falling with the downlink. This is, as you know, the frame. Here is the duration is different because the SCS is using 30 kilohertz and this 15 kilohertz. That's why you will have here within this one you will have 20 slots within the so each subframe, this one will be equivalent to 2 slots within the 5G network. So you can see here the 4G is downlink. Now it's being equivalent to downlink, and same for here. And even for special slot, part of it is downlink, and the other part is for flexible and slot. And here also need to align again the special pattern or special slot, SSP, special slot configuration as well. But you can see also uplink is being aligned, downlink is being aligned. So this is the first solution, can be shifted by 3 milliseconds and using this 8 to 2. The second one, you can keep the exact without 0 frame offset, but in this case, you need to change this kind of pattern. For example, here you need to give it as 4 to 4, and you need to configure now a dual period. For example, period 1 and period 2, 4 to 4. So what you need to do, so you give 4, which means 3 downlink, 1 flexible, and 2 uplink, then would be 4 downlink, then it will be repeated again. So for example, can be the configuration being configured. So in this case, again, this will be completely aligned. As you can see, there is no any misconfiguration between the uplink here. And again, within this flexible and downlink, you should be aligned, right? So, for example, this one here, the special subframe is having 14 symbols, while this one will having a 28 symbols, because if each slot will have a 28 and the slot is open 5 milliseconds, while the subframe here is 1 millisecond. So as you can see here, this subframe having 14 symbols, 1 millisecond. So this is equivalent to downlink and 1 flexible in the 4G side. As you know, this one, the first one will be all the 14 symbols will be for downlink. So we don't have a problem. This one here, as you can see here, the first part, for this part, we're using this settings, the 4G is using 10. So having a 10. So if you configure here, the first 14 will be equivalent to that part. Then the second one, which is the second part here, from the fixed here, the first one here will be 14, which is being aligned with the first part of the 10. Then the second part of flexible here, for this one you will be using 644 to align with this kind of configuration. So starting from this one will have 1, 2, 3, 4, 5, 6, which is equivalent to 3, and the same for the uplink and guard band as well. So now we have a complete alignment, and this is what it means by aligning the frame between the 4G and 5G. And this is mainly whenever you are using the same frequency for both of them. If you're using a different frequency, assume that you have 4G in TDD 2.6, and you have NR in 3.7. So in this case might not be really required. So now let's jump to the last. Let's now jump and go to the last and very important part about kind of planning and impact of the latency or the performance whenever you change the slot format configuration. So as you can see in this figure, the slot format configuration can directly impact four different parts. First one can be the throughput, second can be latency, and can be coverage, and can be RACH planning as well. So let me first explain this kind of latency, RACH planning, and coverage. Latency part, for example, assume that you are giving a different slot configuration. Okay, for that part, assume this is your slot configuration as you can see here. So you are using 4 to 4. So the uplink would be coming at this particular slot. So for example, assuming now you have a downlink transmission. So for every downlink packet, right, being received by the user, you need to acknowledge this packet, right? So you need to send out the acknowledgement. So you need to wait until he received the time of switching from downlink to uplink to transmit the uplink acknowledgement here. So this is the delay which being so this can be impacting your RTT. So in this case, for example, you have 8 to 2. So you have to wait, instead of waiting, for example, 3 slots, now you have to wait. If you transmit downlink here, journal B, you have to wait until they here to transmit it. If you're using, for example, this kind of configuration, which is 3 to 1, which is 2 downlink and 1 flexible uplink, you can see that now it's even more quick feedback will become in the uplink. And as a summary for that, different slot format in general allocation can influence the downlink hard feedback, which is being sent in the uplink data, and also the scan and uplink data scheduling in general. Uplink data also can be more quick being sent whenever you having a slot format coming in the beginning. This is also can improve reduce the RTT delay in general. The second part, it can also improve the shorter SRS transmission period, right? Because SRS usually is coming in the flexible or coming in the uplink. So in this case, you can have a more shorter or more quicker SRS, as for example this particular case here, and this can improve the performance of the MIMO or the massive MIMO performance in general, because SRS sounding reference signal, whenever it's coming more, having more reliability, this can improve the performance as well. The second part is about the RACH planning here. Actually, have two different combination or planning for RACH, right? Which can be long or short. Or short planning. The long preambles or short preambles, long preambles require minimum 2 continuous slots, which is having 1 millisecond. It requires 1 millisecond, which means it requires minimum 2 slots. So if you use, for example, this particular configuration here, this means you cannot use it, or this configuration. For example, assume now you have this one DDD SU, and this is repeated every time. So in this case, you have only 1 slot for uplink. So this case would be open 5 millisecond only. So this case, long preamble will not be supported. So you need to take care whenever you are doing the planning for slot or RACH planning as well. And the same here, if you're having 2 for uplink, this means the long preamble now is being supported. And long preamble is very useful whenever you have a macro site, and especially for macro sites, because it's having a larger root sequence index. So this can give you a much better RACH performance. This kind of short preamble can be more beneficial whenever you speak about the milliwave. It will be for that. It will be can be done because you have milliwave. Particularly, it might be used only for small cells and require less cell radius, while the long format having higher cell radius. The third part is about the coverage. As you can see in the coverage here, I'm giving 3 different slot format and the configuration, a slot assignment configuration. As you can see here, the first part, I'm assuming you have 8 to 2. So we're having 7 slots for downlink, then 1 for mixed between uplink and downlink. So as you know, the SSP is using 4 symbols, right? And usually transmitted, so we are supporting up to 8 SSP, right? Being transmitted in for the SSP beam swapping. So this usually transmitted in the first 5 millisecond or the first 4 slots here. It can be repeated again, but in the first 4 slots, as you can see, and every slot will having 2. So as long as you have enough slots here, you can transmit and get up to the maximum SSP. This is in case of your network supporting this SSP, 8 SSP. And the second case here, for example, assume you're having DDSU. So you can see here, you have 2 slots for, you have 3 slots for downlink. Then number 4 will be mixed between downlink and uplink. So this also depends. You can have even up to 6 or 7, depend on how many symbols here is being used for downlink, because downlink needs the SSP needs at least 4 symbols, right? So this is the symbol number 8 will not be used because this one is partially used by downlink for slot number 3. So you have only maximum up to 7, and sometimes it can be even 6 if you're having a list symbol within this special slot. This is one case. The last case here, and whenever you have a less SSPs transmitting, this can impact your coverage, SSP coverage especially, because you'll have, instead of narrow beams, you'll have more wider beams. So this can impact even the quality or the coverage. The last part here, it's as you can see, it's using DDSU, so it's 2 downlink and 1 special. So this is can use up to 5 SSP, even sometimes can be 4. So this is also having less performance. Now, how this can impact the performance for the downlink or uplink throughput? As you know, there is allocation ratio, right? We can give a ratio between downlink and uplink. So assume, for example, for this pattern, it's using DDSU and it will be repeated. For example, this 2 milliseconds will be repeated 5 times. So this is, for example, the ratio which you have it. If you calculate the number of total downlink symbols, I will show you now quickly how I calculated this. Downlink symbols is 280. So, and this is the downlink of the main symbols used for downlink, for example. How many? 105. This is equivalent to ratio of 70, and you will have 25 for percent for uplink. So 70% of the resources or symbols within the frame, it will be used for downlink, and 25% for uplink, and the remaining will be overhead or SRS. And for example, for this particular case, second one, it's having higher ratio in downlink, means that this one can give much higher speed in terms of downlink, and this one have a much lower speed in terms of uplink and very high speed in terms of uplink. So as you know that this is a factor of throughput, let me quickly take you through the calculation about that part, how I made the calculation and how it can impact the throughput. I will show you, like, if you change this value, how it can impact the throughput. So as you can see here in this table in the middle, this is one which I was showing in the slides. As you can see for this table, I have a different patterns here. For example, the DDSU. So here, how I calculated the 280. This is 280 is simply, if you are using SCS 32 kHz, it will be equal to the 20 slots. You have 20 slots multiplied by the 14 samples. This is the total number of samples which you have here. The downlink of the MA symbols, for example, this is a formula which is being used. For example, this will be equal to the number of samples per slot. For example, how many samples you have in per slot, multiply. So the number of samples is fixed to 14, right? So the first part here, it will be 14. Let's put this one here. So the first one will be 14 as showing in the top left here. The second part here as showing is asking you for the number of downlink slots. As you can see here, how many downlink slots you have? You have 2, right? 2 downlink slots. So this one will be multiplied by 2. Then it will be multiplied by repetition within 10 milliseconds. So the repetition will be, you have 2, and this is like 2 milliseconds. So it will be repeated 5 times. So we need to multiply again by 5. Then it will be plus the special slot here. How many special slots you have? For example, this is plus the flexible slots. Consider this is for uplink. This is if you are speaking about downlink. This will be plus number of downlink samples within the flexible slots, which is how many samples you have. You have 11 for this particular configuration, so you multiply by 11. And how many number of slots you have in general for S? You have only one S, so it will be multiplied by 1. And this will be repeated again for 5 times. So this will be the configuration, and you apply the same here and there. And for the throughput, for example, assume now I'm using this kind of DDSU, which is the first one. If you look into this speed now, it's like saying as 1.2, for example. If I change it to, let's start first with this first one here. DDSU, this is showing as 70%. So this is changing this kind of value down here for this one, DDSU. So if I change this one, and now it's giving, because you have the overhead or the downlink to 70%. So now it's changing, for example, for this particular configuration, which is DDDSU 1131, this one. So now I'll change this one to be DDSU. So you see now the throughput increase because you have 6% higher in downlink. However, the uplink will be impacted compared to the previous one. And actually, this is the end of today's session. I hope if you like the session to press like and to comment, and I will upload this kind of Excel sheet in the video description. You can go through it and download it and enjoy it, and please share it with your friends, and stay tuned for the next sessions about the remaining for the 5G planning and non-standalone. Thank you, and see you next session.